Good morning. We are going to look at section 6.2b today, continuing to look at that idea of multiplying and dividing radical expressions. Our focus today will be on the dividing type. All right, so just like we had with multiplication, if we have the same kind of index and the A and B inside there represents real numbers, then we can do division just like we did multiplication. As long as the index is the same, we can combine it into one division problem. Okay? And the nice thing about that is if we can then reduce this A over B, we can simplify our expression. So when dividing radicals, we're going to simplify anything that's outside the radicals, and then we can also reduce the fraction inside. We divide the numbers out just like normal, regular fraction. And remember, our rule for combining variables when you have some in the numerator and some in the denominator is that we subtract our exponents. So we're going to simplify these using our rules of radicals. Remember, we're still assuming every variable is a positive number, so we don't have to worry about the even, even, odd rule. All right, so for the first one, notice they are both square roots. So I'm going to rewrite this as one big square root. I have a 2x to the 8th in the numerator, and I have an 18x cubed in the denominator. And then I'm going to look at the front numbers, those coefficients, the 2 and the 18. I could reduce that to 1 and 9. I'm looking at the x's, and if I have 8 of them on the top and 3 on the bottom, I have more on top, and I have an extra 5 of them. If I took 3 off of both, I have an extra 5 in the numerator. And now we're going to simplify this just like we've been doing. We can look at our x's and say, how many groups of 2 can I make out of those 5? The square root of 1 is just 1. The square root of 9 is 3. And for my x's, I can make 2 full groups, and I still have 1 left over. So my simplified answer here would just be an x squared root x all over a 3. If you want to leave the 1 in front, you certainly can, but it's not needed. For our second one, notice we have cube roots for both, so we're going to put it all into one big cube root. All right, I can reduce the numbers that are inside. I can take 162 and divide by 3, and I get 54. And I can look at my y's and say if I have 5 on top and 2 in the denominator, I have an extra 3 in the numerator. And notice on this one, I don't have anything left in the denominator. All right, simplifying it like we've been doing. We're looking for a perfect cube in 54. 27 does go into 54 2 times, and the cube root of 27 is 3. So for the 54, we would break that into 3 times the cube root of 2. For the variable part, remember we're looking for groups of 3, and we have 3 of them, so we can make one full group. So our answer would be 3y times the cube root of 2. All right, notice on this one, we have some numbers that are outside and we have some numbers that are inside. We can reduce the outside ones. So 9 divided by 3 would be 3. And then I'm going to put all of this stuff inside one big square root symbol. And try to break that down. I can reduce the 50 divided by 2 to 25. I can look at those x's and say, well, I've got 2 on top and 6 on the bottom, so I have 4 left in the denominator. Looking at my y's, I have 9 on top and I have 1 on the denominator. I can reduce that to 8 on top. Okay? We are trying to do a square root. And we know that the square root of 25 is 5. Again, groups of 2, and I have 8 x's. That means I can make 4 full groups. And in the denominator, I have 4, sorry, those were y's. In the denominator, I have 4 x's. I'm doing groups of 2. That means I would have 2 left, 2 full groups. So simplifying now, the 3 times 5 would be 15, y to the 4th over x squared. When simplifying radicals, sometimes we're left with radicals in the denominator. When we have that situation, we have to do something called rationalizing the denominator. It's a process of rewriting an expression so that there's no radicals left in our denominator. So our first step is reduce the fraction. Maybe we can get rid of some of the stuff and end up with no denominator at all. For the numbers and each variable in the denominator, we need to identify how many of each are missing to make the radical complete. In other words, if we are taking an nth root, we need n of those things. So let's say we have an x here. We would need n x's to make a full group. Okay? Now, what if we have more than n? Well, then we have to bump it up to the next multiple. We want to have full groups to be able to take out. We're going to multiply the top and bottom of the fraction by whatever missing pieces we need to make these complete groups. All right? So the idea is we don't want any leftover pieces in the denominator. So our first example, it says write each radical expression in simplest form. All right, so the first thing I would notice is they're both fourth roots, so that's good. The second thing I would notice is that one is a 2 and one is a 3, and there's no common factors, so I can't really reduce that. Okay, so then I go to say, well, I have to get rid of that fourth root of 3 in the denominator. I only have one little 3 there, and I'm trying to make groups of 4. So that tells me I need 3 more of them. So what I'm going to do to rationalize this is I'm going to multiply by a fourth root of 3 cubed. So now I'm putting 3 more 3's in the denominator to make 4 total. And whatever I do to the denominator, I also have to do to the numerator. All right, let's clean up the denominator first. We have a fourth root. We have 1 3 in the first one. We have 3 more in the second one. That means we have 4 of them now. So I've made one full group, which means the denominator is just going to come out as one full group of these 3's. For the numerator, I had a fourth root of 2, and I have a fourth root of 3 cubed. Well, 3 cubed is 27. Okay? So I would have to now put that together into one fourth root symbol, and 2 times 27 is 54. Now, if there was a perfect fourth in 54, I would try to pull that out. There isn't one, so we are finished with that example. All right, my next example here, again, they're both the same kind of index, so we have cube roots. I'm going to put this together and try to reduce what I can. I have x's in the numerator and y's in the denominator, so I can't get rid of any of that. But I can reduce the 14 and the 10 by 2. So I'm going to think of this as the cube root of 7x over 5y squared. Okay, now we are trying to do groups of 3. That means we need 3 of all of the pieces that we have in our denominator. So we're going to look at what do we have to multiply in there to make full groups. Well, we have 1 5, so we would need 2 more 5's to make a group of 3. I have 2 y's already down in the denominator, so I really just need 1 more to make that a full group. And again, whatever we multiply to the denominator, we have to do the same thing to the numerator. All right, so now we have the cube root. On top, we have a 7x times a 5 squared y. Well, 5 squared is 25. 7 times 25 is 175. We have 1x and 1y. Neither of those are big enough to pull a full group out. And looking at the denominator, I have 3 5's now, and I have 3 y's. So I can make a full group of each of those. So my answer is going to be the cube root of 175xy divided by a 5 and a y. We're making full groups of those. Okay? And again, if there was a cube root in 175, we'd want to pull that out. There is not a perfect cube from in there. I know that because I had 1 7 and I had 2 5's. None of those have overlapping factors, and I don't have 3 of either one. All right, our next one, we have the cube root of 5x squared over 6y squared z. Nothing can be reduced there. 5 and 6 don't have any common factors, and my variables are not the same in the numerator and the denominator. So we are trying to do groups of 3. We need to multiply in here things to make 3 of things in the denominator. I have 1 6 here, so I'm going to need 2 more. I have 2 y's, so I need 1 more to make a group of 3. And I just have 1 z, so I'm going to need 2 more z's to make a full group. Okay, so numerator. I have 6 being squared, which is 36, and 36 times 5 is 180. For the x's, I have 2 of them. I have 1 y, and I have 2 z's. But the nice thing now is in the denominator, I have 3 of everything. I have 3 6's, 1 here and 2 more here. And when I cube root those 3 6's, I'm just going to get a nice 6. I have 2 y's here and 1 here, so I have a total of 3. And I have 1 z and 2 more. I have a total of 3 of those. So it's going to clean up nicely. I have the cube root of 180 x squared y z squared for the numerator. Denominator comes out as 1 group of 6, 1 group of y, and 1 group of z's. All right, go ahead and pause the video and you try this next one. All right, let's check what you did. Looking at the 7 and the 8, there are no common factors there that I can reduce out. I have an x in the numerator and a y in the denominator. Now for this one, you might have looked at this and said, okay, I need I have 1 8, so I would need 4 more 8s to make a group of 5. However, if we think of this 8 as being 2 cubed, we can think of it as having 3 2's already, so it's not as much that needs to be multiplied in to make a group of 5. All right, so let's look at this as the 5th root of 7x over, instead of that 8, I'm going to think of it as 2 cubed, and I have a y squared there. So to get a group of 5, I would need 2 more 2's, and I would need 3 more y's. And I'm just going to extend that 5th root symbol to put all of that under a 5th root. All right, for the numerator, 2 squared would be 4, 4 times 7 would be 28. I have 1 x and 3 y's. Neither of those are big enough to take a group of 5 out. In the denominator, I have created a group of 5 2's. So when I take its 5th root, I have a 2 left. And I have made a group of 5 y's. When I pull that out of the 5th root, I get 1 full group. All right, so on that example, we were trying to reduce how much we have to put in. In other words, if you had put in 4 8's to make a group of 5 of them, you would have things that you could later then divide out, factor out, and take their roots. So we do want to try to put as little in there as possible so we have less to simplify at the end. All right, our last example of this type, we have cube roots again. My coefficients are 7 and 2. There's no common factors there. But notice that I do have some overlap in terms of variables. So let's clean this up to see what we really have left. We have a 7 over 2 for our coefficients. Looking at our x's, if we take 1 off of each, we just have 1 left in the denominator. If we look at our y's, we have 2 in both the numerator and denominator. They're going to just reduce out. And if we look at the z's, we have 4 in the numerator and 2 in the denominator, so we can reduce that to having just 2 in the numerator. Now what that did for me is it cleaned up how much I need to actually put in here to make this perfect. All right, so let's put in, we need groups of 3. So I have 1, 2. I need 2 more to make a group of 3. I have 1x. I need 2 more to make a group of 3. Simplifying. We have 7 times 2 squared. 2 squared is 4 times 7 is 28. I have an x squared on the numerator and a z squared. And in the denominator, I now have 3 2's and 3 x's. So this will clean up. I'm still going to have that cube root of 28x squared z squared for the numerator. But for the denominator, I have 1 full group of 2's and I have 1 full group of x's that I can take out. Okay? Our last example. It says the following rectangle has a side length of the cube root of 3 and an area of 9 times the cube root of 7. What is its width? Well, yesterday we talked about the area being length times width for a rectangle. So if we are given length and area and we're trying to find width, we just have to take and divide out that length to the other side. So we're really just being asked to take the area divided by the length. So we have 9 times the cube root of 7. We are dividing by the cube root of 3. Okay, now notice that 9 in front is just going to sit out there in front. The cube root part that we have is this 7/3. Okay, so we need to multiply in enough that's going to make this a group of 3. So I need 2 more 3's in the denominator since I have 1, which means I have to put 2 more 3's in the numerator. So I have a 9 times the cube root of 7 times 3 squared. Well, 3 squared is 9. 9 times 7 is 63. And I'm dividing by the cube root of 3 3's. I have 1 here, 2 more here. I have 3 3's. Well, the cube root of 3 cubed is just 3, right? We have 3 of those, so we can take its root. And now, notice that I have numbers out front that are both outside of a cube root symbol. So I can reduce this to just being a 3. So I have 3 times the cube root of 63 for my width. All right, so let me know if you have questions. Otherwise, your assignment will be worksheet 6.2b.